My name is John Lorden, and I've been looking into hundreds of unsolved mysteries over the past 5 years on my YouTube channel, Lorden Arts. And I've been known to bring a respectful, victim-focused approach to the stories that I cover while donating thousands of dollars directly to those cases and the charities that help them. Now, I'm bringing that approach and sensibility, along with some of the biggest mysteries I've ever looked into and some new ones, to a weekly podcast called Seriously Mysterious. From bizarre occurrences to unsolved murders and unexplainable disappearances, everything is fair game on this show as long as it's seriously mysterious. You can find Seriously Mysterious on your favorite podcatchers or by visiting seriouslymysterious.com. Let's look into the mysterious together.
From the flickering flames of ancient torches to the gas lamps of the 1800s, humanity has always sought ways to banish the darkness that covers our nights. The 1800s was a time when electricity was a new and mysterious force, and people were still trying to figure out a way to harness its power. And this is where an idea was born, one that led to the dream of a future in the glow of electric light. And this was even before Thomas Edison's invention of the light bulb. Welcome back, friend, to Hometown History. In today's episode, we will explore the work of Charles Brush, the man who revolutionized the way we light up our world. Charles Brush's journey started in a town called Euclid in Ohio. He grew up on a farm not too far from Cleveland, about 10 miles away. He was a farm kid through and through, but he wasn't just into that. He was more interested in science. When he was just 12, he started playing around with simple electrical gadgets and even created actual working projects. In fact, when he was only 12 years old, Brush made his first static electric machine using random objects he found around the farm: a bottle, a piece of leather, and amalgam from an old mirror. It was clear to those around him that Charles was gifted and had an aptitude for science. He was mainly inspired by Humphrey Davy, a famous scientist around his time. Now in 1802, the esteemed Humphrey Davy conducted some experiments at the Royal Institution, creating the most potent electrical battery known at the time. And with this, Davy achieved a momentous breakthrough: the creation of the first incandescent light. This involved passing an electric current through a delicate platinum strip chosen for its resistance to high temperatures. The only problem was that the resulting light had limitations in brightness and durability, but it still served an important demonstration of the fundamental principle: the generation of light through the passage of electric current. Building upon this achievement, by 1806, Davy introduced a more impactful form of electric lighting to the distinguished Royal Society in London. This innovation was basically an early version of the arc light and laid the groundwork for subsequent developments in electric lighting technology, like ones made by Charles Brush. Coming back to him, Charles went to Central High School in Cleveland, and that's where he made his first arc light lamp. Most of his work was a continuation of this, so it's important to understand what arc lights are. An arc lamp, or arc light, is basically a type of lamp that generates light through an electric arc, which is a flow of electric current between two electrodes. Before the advent of electric lighting, various sources, such as gas lamps and candles, were used for illumination. Still, they had their limitations, like practicality or brightness. This is why Humphrey Davy developed the carbon arc light, which marked the inception of practical electric lighting. However, it was still a relatively new invention, and it did not address the need fully. So to develop his first arc light as a high school student, and you will agree it was a pretty early start for him, he used resources from the school lab, created a battery using zinc, carbon, and nitric acid, and crafted carbon electrodes from gas retort carbon. He mentioned that forming electrodes from retort carbon was a challenging process. Nonetheless, his teachers were highly impressed, leading him being entrusted with overseeing the electrical equipment at school. This responsibility not only showed his skills, but also granted him unrestricted access to the physics lab, which he seemed to utilize effectively for the good of humanity. During their remaining time in high school, he discovered the work of Wilde, who conducted experiments with a dynamo and arc light in London in 1866. His dynamo was a type of dynamo electric machine, where he used electromagnets, leading to a significant increase in power. This machine was a major development of his time, as Wilde showcased its capabilities through impressive demonstrations, like melting iron bars. As a curious mind, Brush was inspired by those experiments, and we see that in his work. He graduated from high school with honors in 1867, and even his graduation speech was called The Conservation of Force. In his speech, he discussed the conservation of energy, tracing its path from the sun to various sources, like vegetation, coal, steam, electricity, and ultimately, light. I would say this was the beginning of his journey into the world of electrical innovation. But the beginning was way back when he was 12 years old. Now, he was only getting better. After completing his high school education, Brush wanted to pursue higher studies. Unfortunately, his parents lacked the financial means to support his college education, having already expended their resources on his high school expenses. Yet as luck would have it, Charles's maternal uncle stepped in and agreed to finance his education through a loan. After all, they were all well aware of his sharp mind and love for learning. With his uncle's encouragement, Brush chose the University of Michigan for his higher education, enrolling in the fall of 1867 to study mining engineering. At that time, the university didn't offer courses in electricity, and commercial opportunities in this field seemed limited. So Brush believed that mining engineering would equip him with practical skills, ensuring future employment to repay his loan. Despite the absence of electrical coursework, Brush's variety of courses, including mathematics, science, and engineering, provided him with the knowledge necessary for his future achievements. Balancing a hectic schedule, he managed to complete his studies ahead of schedule and graduated from the college in June 1869. But his educational career didn't stop there. He then went on to get his PhD at Western Reserve, now known as Case Western Reserve University, and graduated in 1880. But before he graduated, he made his name in history with the creation of a lighting system. In 1876, Brush started a new project and ended up securing support from the welding supply company in Cleveland to design his dynamo. It was basically an electrical generator that would be specifically crafted to power arc lights. He initially drew inspiration from Zenobie Graham's dynamo design, the Graham machine. Now this was an electrical generator designed to produce direct current. However, Brush's final design was significantly different, and in his patent, he outlined the need for a distinct approach. He aimed to address shortcomings he identified an existing magneto-electric apparatus, like their size, heavy weight, and high cost. So Brush's innovation aimed to create a more efficient and manageable electrical generator system. Even the Franklin Institute of Philadelphia validated Brush's efforts, declaring his dynamo superior after rigorous testing in 1878. They too emphasized that the simplicity of design and ease of maintenance set Brush's dynamo apart from others. Now, the dynamo operates through a systematic process. At its core was a coil of wire, the armature, which was capable of rotating. Around this coil was a magnetic field, created by powerful magnets. The dynamo was connected to an external source of mechanical energy, like a steam engine. So as the armature rotated within the magnetic field, according to Faraday's electromagnetic induction principle, it induced an electromotive force, or voltage, in the coil, generating an electric current. To maintain a continuous current flow, Brush incorporated a commutator, a rotary switch that reversed the current direction. This alternating current was then collected by brushes touching the commutator and conducted out of the dynamo. And if you really think about it, the dynamo transformed mechanical energy into electrical energy. And this concept laid the foundation for the practical use of electricity in the late 19th century. It showed the capability to generate a continuous and controllable electric current, and this was a crucial step toward powering electric lights and other electrical devices. Even Edison's subsequent development of the incandescent light bulb can be associated with this. The establishment of power distribution systems was also built using the dynamo's principle. Brush's work demonstrated the feasibility of large-scale electrical power generation, influencing the construction of power plants and the widespread adoption of electric lighting in homes, businesses, and cities. Now the question is, how exactly was this dynamo connected to his lighting system? After he successfully created the dynamo, the next step included enhancing arc lights. He had already been working on that for a long time, pretty much since high school, so he had already created the basic structure. Yet these lights faced challenges in becoming commercially viable due to their unreliability. The light produced by arc lights occurred when a spark jumps the gap between carbon rods. But the problem was, these rods wore away at their tips. Now, to maintain a steady light, the gap between the rods had to be consistent, which made it necessary for frequent manual adjustments. So after he had the power source, he tried to come up with a more precise mechanism to address the issue with the lights. So as I just mentioned, the wear and tear on the rods demanded frequent, risky manual changes. So in a strategic move, Brush introduced 2 sets of rods in each lamp, along with an electrical regulator that automatically switched from used to new rods. It might seem like a minor change, but it helped on multiple fronts. First and foremost, it enabled continuous illumination by ensuring that when one set of rods wore out, the electrical regulator transitioned to the new set, removing any interruptions in the lighting. Besides that, it significantly reduced the need for frequent manual changes of carbon rods, which in turn enhanced operational efficiency. With this, the safety of maintenance personnel could be ensured. So owing to this simple step, the lights became appropriate for use in public lighting in cities. This is also because of the electrical regulator, which played a role in maintaining a consistent gap between the carbon rods, which meant stable and reliable lighting. But this was not the only thing that had to be changed. Brush also encountered problems with excessive flickering. caused by low-quality carbon rods. So to resolve this, he crafted higher quality rods, using byproducts from Rockefeller's Standard Oil. His final version consisted of an arc lamp powered by a dynamo that generated electricity. The lamp had a clever mechanism involving a solenoid, which is a coil of wire, and a ring clutch, which automatically controlled the gap between the rods and the lamp. This ensured a stable and bright light without the need for constant adjustments. For situations where multiple lamps were connected in a series, Brush designed a cutout device, a device that ensured that if one lamp failed, the others in the series could continue working. So with all the improvements and modifications in place, Brush's electrical lighting system became practical, reliable, and suitable for widespread use. In 1879, Brush's experiment to light a Cleveland park with arc lighting was a success. This was the first attempt at electric public street lighting in the world. Following that, Brush attempted an experiment to light an entire town. In 1880, Brush traveled to Wabash, Indiana, and was contracted to install a free 2-week experiment to light the entire town. If it was successful, the town would buy the entire lighting system for $1,800. 4 3,000 candle power lamps were used and placed atop the courthouse, which sat on a steep hill overlooking the town. The lights were a success, and the town purchased the lighting system. Now, as Brush's lighting technology gained popularity, he continued to work on improving the efficiency of battery manufacturing. It helped smooth out fluctuations in demand for his dynamo's power. Over the subsequent years, Brush continued to enhance his arc light design, obtaining additional patents. His systems were adopted by several cities for public lighting, with Philadelphia's Wanamaker's Grand Depot among the notable installations. Brush's lights had easier maintenance, automatic functions, and double the lifespan compared to Loblakoff candles. In addition to that, his generators demonstrated reliability, automatically adjusting voltage with increased load while maintaining a constant current. In 1880, the New York Central Power Plant dynamo, powered by Brush's innovation, began lighting a 2-mile circuit. This was a major win for him. Simultaneously, the San Francisco system became the pioneer in selling electricity from a central plant to multiple customers through distribution lines. Yet another groundbreaking development facilitated by his work. By 1881, major cities including New York, Boston, Philadelphia, Baltimore, Montreal, Buffalo, San Francisco, and Cleveland were using Brush's arc light systems, contributing to public illumination well into the 20th century. But after almost a decade of success, Charles Brush exited the industry. After his remarkable innovations were eventually surpassed by larger organizations with more extensive research and development capabilities. In 1889, Brush Electric Company, a company he started in the year he earned his PhD, was acquired by Thomson Houston Electric Company. Within 3 years of this acquisition, Thomson Houston merged with a company specializing in incandescent lamps. And yes, that is where Thomas Edison came into the scene. This was a lighting system that would surpass arc lights, leaving Charles Brush's name in the shadows. This merged company then adopted the name General Electric. Now, even though he was out of this industry, his legacy extended beyond lighting systems. He was the one who built the world's first automatically operated wind turbine, a 12-kilowatt dynamo to power his mansion, built on Euclid Avenue in Cleveland. It showed his commitment to sustainable energy, as well as his continued aptitude in science. And as years passed, Brush's explorations continued. They included claiming the discovery of a new gas, etherion, in 1898, which was later identified as water vapor. Between 1910 and 1929, he wrote several papers exploring a unique version of a kinetic theory of gravitation based on electromagnetic waves. He introduced the idea of an ether, a substance filling space with special energy waves. These waves, unlike regular waves, don't create heat. According to him, when things fall, they take energy from this ether. So in a sense, he explained gravity as a push instead of a pull, where waves are pushing things together, which is definitely an interesting way to look at it. But he passed away before he worked on this aspect any further. The legacy of Charles Brush has endured through various tributes and institutions. Charles F. Brush High School in Lyndhurst, Ohio, proudly carries his name, with its sports team and groups known as the Arcs, in homage to Brush's revolutionary lamp. The distinctive collars of brown and gold further symbolize his influence, as they represent innovation, wisdom, and the pioneering spirit embodied by him. The Furnace Run Metro Park in Richfield, Ohio, received a meaningful donation of land from the Brush family and is now known as Brushwood. It essentially preserves his memory in a dedicated space. Yet despite these dedications, Brush's work has not received the same amount of recognition as others like Thomas Edison. But that does not mean that his work was not as important as theirs. In a sense, his work set the stage for the widespread use of electric lighting that would follow long after his time. Now, even though arc lights were widely used in the late 19th and early 20th centuries, the concept is applicable in modern times. The fundamental principle of electric arcs, as shown by his invention, has influenced the development of various lighting technologies, including certain types of high-intensity discharge lamps and welding processes that utilize electric arcs. High-intensity discharge lamps, such as metal halide and sodium vapor lamps, operate on the same principle of creating an electric arc between two electrodes within a gas-filled tube. This arc produces intense light, making these lamps efficient for various applications, like street lighting and industrial settings. Even the understanding of arc phenomena in electric currents has played a role in advancing today's technologies, like plasma cutting, a method used to cut metals very precisely in industries. So Brush's pioneering work with arc lights is a fundamental element in the development of lighting technologies and continues to impact modern applications across various technological domains. And that's it for today's episode. The takeaway here is that Charles Brush's lighting system may not be a household name, but its brilliance echoes through the ages of time, reminding us that even the smallest sparks of innovation can light up the world. Thank you for listening to Hometown History, and be sure to follow along for more interesting stories from the past.